So I'm here to talk about something, a really interesting topic, I think, because when hybrids first come out or when you first hear of them, of course you want to know what's special about this technology. I mean, that's the right question to ask. And oh well, it does this and it does this and it gains you fuel mileage, and you hear all these nice things, and you always hear someone say, oh, and it has regenerative braking that recharges your batteries while you drive, and you're like, oh, well, that sounds really smart. I mean, who would want to recharge their batteries while they're driving? And it's sold in various ways, of course, depending on the technical knowledge of the person talking about this at the particular time. So I wanted to phrase this discussion in the sense of this question: is it a cool technology? Is it something new and exclusive to it in and of itself, or is it a marketing tool? And if it's a marketing tool, it's not to say that that's not a cool technology at all. It's rather to say, is it something that already exists? We're just kind of getting a little extra kick from it. I wanted to phrase it this way too, because I think that if you had a group of students who were even slightly interested in hybrids, it'd be a good way to phrase the lesson is with these questions, is to ask, is this something new and unique, or is this just something that's kind of repackaged to make it sound neat? And if it's repackaged to sound cool, that's great too, because that shows students that you can take something that's already existing and apply it and talk about it in a new way to attract people to its use. And that's all. That's a good thing. So let's delve into this a little bit. First of all, you probably have heard this in a few different times over the past couple of days, but I'll reiterate some of the highlighted points of why does hybridizing a vehicle improve miles per gallon. First of all, it downsizes the engine, which allows us to run in a more efficient zone, and I think I mentioned that last time I talked to you. Also, with adding the electric motor, we get this nice torque curve, and you can see that at 0 RPM, it has its maximum torque, and it goes out to some base speed before it falls off. That property is really advantageous when you've got a vehicle that's doing a lot of stop and go, that maximum torque. Of course, if you look at a gasoline engine, it looks nothing like that curve. It looks completely different. It always has to be at idle or greater, and at idle it has almost no torque, and at wide open it has a much smaller torque. So there's a significant advantage right there. Also, the efficiency, if you look in this peak island here, we're talking 90%. You'll never see that in a gasoline engine. Aerodynamics is another way in which hybrids improve, but I always have to put a little asterisk next to that and remind people that that's not something that's exclusive to hybrids. This is something we've paid more attention to, I guess, with hybrids. If you look at the Insight, it looks very streamlined, very teardrop. And let's be honest, Honda had to do that. They had to make this thing as maximally efficient as possible so that they could get these 90 mpg numbers so that everybody went, what is that? What is that technology? Had to do that as kind of an upfront selling point. And so they went all out. Now we look at hybrids like that and we laugh at them and say, it's not a very good looking hybrid compared to mine, haha. So this has become, it's kind of fallen back into mainstream, but it is something that comes into play. We can plug in for electric power recharge, and that's becoming more and more popular, is the idea of, like the Chevy Volt that we looked at last week. You can take it and plug it in either to a standard outlet or to a higher power charging outlet, and we can bring in electric power, which if you look at the energy to energy comparison, the plug-in is significantly cheaper, cost-wise at least. And I'm kind of trying to say things specifically because if I get into larger effects, then we start to balance this, okay, source of gasoline versus coal energy versus nuclear energy. It gets really complex once we go past the cost point, right? So from a consumer standpoint, if they're specifically looking at how much money's coming out of their wallet, this is going to look like a really cool feature. Wow, that's a lot cheaper for me to get to work and back. No argument. Cannot defeat that point. And then finally, one of the ways that hybridization improves MPG is through this regenerative braking. And what you probably know if you know nothing about this topic is that that means that as when you hit the brake pedal, the car doesn't just burn all that energy into heat, it turns some of it back into electrical energy and puts it in the battery, recharges the battery, and hence the regenerative part of it. So the idea this morning is to delve a little bit deeper into this and answer this question: what is regenerative braking? And is it a technology that's added? Is it something that we have to add on to a hybrid in addition to the electric motor and the batteries and the power electronics? Or is it just already there and we're just talking about it in a cool way? So the first thing we have to talk about is how electric motors work. And this is, by the way, I had to skip a few things here because this is an hour and a half lecture when I give it in a class. So I jump forward a little bit to this point that how electric motors work. Well, first of all, we have force in opposite directions around a rotational object that creates torque. And as a quick visual, we've got just a couple magnets around the stator, which is a stationary piece, and the rotor, which is the rotationary piece. And if we create a magnet on that rotor anywhere, then this magnet and this magnet are going to interact to make it pull this way, and this one are going to interact to push it this way. So really that's the exact idea. It's force in opposite directions. In this case, it's being pulled this way and pulled this way. I guess opposite directions might be a little confusing, but I'm always thinking things from a physics perspective, equal and opposite forces. And it's around a rotational device, right? So if it were in a straight line, we would just get linear motion. But instead, since this is circular, we get rotational motion. And when we have force in a rotational direction, it's called torque instead of just force. So there you go. There's Physics 101. That's pretty foundational stuff right there. So as soon as you pass that point, of course, everything gets much tougher. And by the way, I always teach this class for mechanical engineers. So we go back to not only electricity, but electromagnetics. And I see the eyes kind of glaze over because even as an EE, it's one of the toughest topics that we talk about. So it's a difficult concept to understand. So I want to boil it down to its really most essential points. The first and foremost, the force is from two magnetic fields interacting, north and south poles. We've all seen that physically. You can easily demonstrate that in a classroom. And that could be two magnets, right, which is easy to do. Just take two permanent magnets and twist them around, and they do all kinds of things, and we can see the patterns really quickly. Also could be one magnet and one coil. And as you probably know, you can take a coil of wire and run electricity through it and make an electromagnet, which acts a lot like a magnet in many ways. So we can have those two interacting, or we can have two coils. And electric motors are basically composed of combinations of these last two. And why the last two? Well, because we can't control permanent magnets. If you put those in a motor, they're just going to go zoop, they're going to line up, and it's going to sit there forever. So that doesn't do us a whole lot of good, right? We need to be able to control an electric motor in a lot of different ways. And especially for hybrid vehicles, we need torque and speed. And as you probably know, there's also stepper motors, which we want to control the position of. And there are other uses or other ways to control the motor. But for driving a hybrid vehicle, torque and speed are the two big things we care about. Oh yes, and in my little image here too, you can see that if you hook the battery to two brushes, which bring electricity into a coil, it can produce a magnetic, what looks like a magnetic field. And one of the cool things to always show students is the right-hand rule. And the students always ask, why isn't the left-hand rule? And you say, because somebody said so. And that's a really good lesson too. I like that one because you can just hear the gears turning. Like, could it have been the left-hand rule? Oh, absolutely it could have been, but it isn't, right? And arbitrary standards are always a fun discussion. Well, but I want it to be the left-hand rule. Okay, so let's try the right-hand rule first. If the coil goes like this, and well, you always put your hand in the direction of the current. So I'm assuming since that's a north pole, that the current is going through that way, and so therefore there's my North Pole. You say, okay, for all those left-handed students in the crowd, you go this way, you follow the current around, and that's your South Pole. Oh, okay, I get it. So they put an N on this thumb, and they put a S on this thumb, and boom, it works either way. Done. It's great. But as you work with students through these kinds of things, it's a fun little distraction to get away from, oh, heavy physics, electromagnetics. Oh, wait, right and left? Oh yeah, I can do this. So we find which direction the pole is facing and where the north side of it is, and therefore which directions the forces are going. These are all things that students with just a basic experience with magnets can figure out. And of course, from here on is where it gets far more complex. But we can at least get them to that point. And so this is what's interesting about it, is that coils can act like magnets, as we just talked about, and they are controllable. So if we use one or more coils, or use coils on one or more pieces of electric motor, then we can control it. We can control the speed and the torque as we want to. And the direction and magnitude of the electricity through it determines the magnetic direction and magnitude. So not only can I determine the direction of the North Pole by using my right hand rule, but the larger the current flow, the larger the electrical energy that's going through that coil, the more significant the magnetic field too. And so, as you can imagine, if you were to take two equal magnets and sit there and play with them, then you're going to get pretty balanced force. But if you then switch out with a different magnetic material or a different size magnet or whatnot, then you're going to get different forces. And that makes sense too, right? A larger magnet is going to have bigger force. So there we go. There's nothing revolutionary to get us almost completely up to speed with electric motors. And also to illustrate something that's interesting about motors that always baffles the mind, is that if you look at this is a close-up of a winding of a motor, of the rotor anyway, and you can see the windings in here. And by the way, these do have insulation on them. People always ask, is that uninsulated? Are they all touching? Like, no, this is not an N=1 turn motor. That wouldn't work very well, but you can't see it very well. But if you follow this bottom trace right here, this bottom wire, it comes down, turns, and goes up into the distance, and it looks like it connects to this, because it does. And what this is neat to illustrate is that it's wound in one direction around here, and then it turns and winds the opposite direction around here. And so the same wire carrying the same current is actually wound a different way through each of these, creating a north and a south pole at the same time. And I always thought that was kind of a neat feature of electric motors, that someone stopped and thought, I don't have to wind every single one of these separately and control every one of these separately. Kind of like the valve train in the car. Thought, oh, well, I got to control every one of these valves manually. Wait, no, I don't, because there's a pattern, and they're all related to each other, so I can put them on a common camshaft, and they can all act together. Well, that's pretty cool. So, and it's also good to have a visual. Also, students often ask me, like, why do we have these big pieces of metal up here? And of course, that is where the magnet is, the magnetic field is concentrated on these. And so we make these wide such that the actual pole of the magnet is kind of spread out. If it's in too small of an area, we get very jerky motion because you're only interacting with the magnet for a very short period of time in a very concentrated region. So you get this. I actually when I worked for General Motors, we used to look at I worked on a Cadillac project for a little bit, and I looked at the camshaft. I just forgot the name of it. But basically, the sensor on the camshaft that monitors the speed of it, and it has a tooth. A lot of them just have a single tooth removed, and when that tooth goes by, they're like, oh, that's where my position is. Hall effect, thank you. Just totally blanking there for the moment. Yes, and so with that sensor, right, you can sense when that tooth is missing, and you go, oh, I know where I'm at top dead center. But Cadillac said, no, that's primitive. And they make this gear with every tooth is a different width, and they can measure it. So within a quarter of a turn of an engine, they can know exactly where the engine is. And by doing that, they can start the engine much more quickly, which was a cool concept. But it's the same kind of idea, is that this is kind of the region of interaction here. where the magnetic pole appears. And so, all these materials come into play, and talking about the materials themselves is really interesting too. It is, why do we choose iron instead of aluminum and da 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 da? Aluminum's nice and light. Well, that's true, it is. And so what everybody is familiar with electric motors is that if you take electrical energy and you put it into them, if I plug in a battery to an electric motor, it spins. We get mechanical energy out in rotational form. Yeah. I mean, even the least experienced student out there can go, oh yeah, that makes sense. Plug it in, boom, and it turns. And they play with an RC car or, you name it, something. But there's also this less frequently understood principle, even though we use it more often than we realize, that if you put mechanical energy into an electric motor, you can get electrical energy back out of it. And so the question becomes, well, how? How exactly does that happen? And a quick way to illustrate this is, you guys know what these are?
Shake flashlights.
Yeah, it's the shake light, right? The shake flashlights. And all you're supposed to do is just take them and tip them back and forth, and the magnet that's inside moves and slides from end to end, and there's a little coil in here. And as the magnet slides through the coil, it produces electricity, it charges up this little battery, and you flip the light on. Done. So if we just break down this for just 1 second, this is significantly different than an electric motor, but the principle here is exactly the same. What's happening here is that the magnet, we're forcing the magnet to move through the field, through the coil. I should be more clear about that. So this coil has no other electrical properties other than the fact that it's a piece of wire wound in a circle repeatedly. There's nothing else special about it. It doesn't have any power run to it. It's not configured in some other confusing way. It's literally just a coil of wire. So it's really easy to demonstrate this principle even without one of these.
Is it wound around a rod of some sort?
It's wound around still a core, right? It still has a ferromagnetic material that it's wound around, yeah. But other than that, it's about as straightforward as it gets. And when we run this magnet through it, magically, electricity starts flowing to the coil, and it goes up here to this little controller, and the controller rectifies it and sends it to a little tiny battery, and then that battery powers my flashlight. Oh, okay. So you play around with this principle a little bit. You talk it through, you can, go to Wikipedia and look up, Faraday's law and Lenz's law, and you can get all these deep into some of these principles. When you zoom back out, the principle is very simple. If you move a magnet through a coil, it produces some electricity. And so I've actually pulled a couple of slides here from some of the lectures that I do, because there's a really simple way to explain this. Maybe there is. I just haven't boiled it down yet. But what's one of the terms that you have to use in some way, shape, or form is flux linkage. And you can call it something else if you want. But flux linkage is this principle that if I have a coil of wire, even an n equals 1 turn, coil of wire, and it exists in a magnetic field, and I move it, well then it creates, we have flux linkage. First of all, I always get ahead of myself on this part. Flux linkage is the coil existing in a magnetic field. All right. So the flux linkage here, it's integral surface area. This is for your advanced calculus students. They go, oh, well, check this out, surface integrals. The magnetic field over the surface of the coil, and so it becomes number of turns n times the magnetic field times the area. So the larger the area of this, the larger the flux linkage, the larger the magnetic field, the larger the flux linkage, and the more turns that I have, the more. So there's a good little mathematical relationship. And so if we work down through this a little bit, we get to the point here where it also depends on the angle, but that's not super critical for this level of understanding. But we basically have this principle that whenever a coil exists in a magnetic field, that it has some flux linkage. And Yeah, I started to confuse, so let me just say this point again. It does not have to be moving for it to have flux linkage. It just exists. So if there's a magnetic field right here and I take a coil and hold it, it has a quantity of flux linkage. And so I can talk about the angles and stuff like this. But the point we have to jump forward to is what's called back EMF. And now if you see the same symbol lambda, now what we're looking at is d lambda over dt. And you can explain that very simply to say this is a change in the flux linkage with respect to time, aka motion. If I move that coil now in the magnetic field, then I get some kind of E, which is back EMF. And I told you there was no way to go beyond that point before it gets really complex. But what happens here is when the magnetic field or the current in a coil changes, and this is talking about two different directions, but we're talking about the magnetic field changing. The coil opposes this change by producing an EMF, a back EMF, or voltage, back against the change. So it actually resists us in the coil. So if I'm holding this coil in this magnetic field and I move it, then the coil is actually going to act in a way such that it resists that movement. And if you have a big enough coil and a big enough magnetic field, you can actually feel the difference between moving it in air and moving it in the field. It's pretty difficult to get that, and you've got to be pretty significantly sized, but it is possible. And so, if we produce voltage in a coil, it's just wire. If we produce some kind of potential difference across that coil, then, as we know from everything in physics, if there's a difference, whether it be high pressure to low pressure creating wind, or high potential energy to low potential energy creating, motion, it doesn't much matter. When we have a difference in electrical potential, which is what voltage is, a difference in, it is potential. We have a difference, we produce electric current. And so electrons move, so the voltage in the coil produces current, and the current is electrical energy. So let's recap this whole thing. We've taken a coil and we've put it in a magnetic field and then moved it, and this has created electrical flow in the coil, electrical energy flow. Okay, that's the tough part. That's the probably 2-day lecture part. Wait, can you repeat all that? Because I didn't quite swallow all of it. Well, understandable. But this is the principle. So let's bring this all together back into the picture of hybrid vehicles. The vehicle is in motion. Yes, true. This is kinetic energy. Now, for some reason, we want to decelerate. Maybe because the guy in front of us just decided to jam on the brakes. Maybe there's a stoplight. Maybe I'm home. Maybe I'm at my destination. Doesn't much matter. For some reason, we need to reduce our kinetic energy. Of course, the wheels rotate with the vehicle, and so this is producing rotational energy. And the wheels are connected to and rotate the electric motor. The motor rotation is, again, the magnets and the coils moving in with relation to each other. So we have this change in flux linkage and this back EMF. It induces current in the coils. And so therefore, in the coils, we have some electrical energy flowing. Now, as you may also know, electric vehicles almost always use AC motors, except in like maybe golf carts and simple things like this. And so we're actually generating AC power. So this current is rectified through power electronics to DC, which is what batteries are, how they store it, and sent to the batteries. So now we have stored electrical energy and in chemical form. And of course, there are other types of hybrids as well. There's, like flywheel hybrids, so you can store it also in rotational form. Again, there's all different ways we can talk about this. But this is what regenerative braking is. Well, yes. Like, whoosh, you guys both threw up your hands at the same time. Let's.
So basically, as soon as you take your foot off the accelerator, which is just controlling the electricity to the motor, it starts regenerating. So it's not really braking.
Yes and no. Now this is where we have to delve deep into electric motors, but I'll give a summary. An induction motor will be different than a permanent magnet synchronous motor, two of the very common ones used in hybrids, because the induction motor has just two coils. And unless you send power to one of those two coils, there are no magnetic fields. They're just pieces of wire. So an induction motor, if you're cruising down the highway and you let off, it's just going to drift. It's going to coast. Versus a permanent magnet motor, which has that magnetic field. You're going to instantaneously get that back EMF and that resistive dragging force. And this is actually a design consideration too for hybrid vehicle manufacturers is when my driver lets off the gas, how much drag am I able to tolerate before they feel like, I just let off the gas, I feel like I'm braking, right? There's just a feeling like, why are the brakes dragging? So, and this is one of the challenges too, is a hybrid car has to drive like a regular car. So yes, it depends on the type of motor, but for the permanent magnet ones, instantaneously. For the induction motor, we can completely control it. Was that your question? You got a different one?
No, I had a
Okay,
question.
go
about
right ahead.
The AC being rectified to DC, is that an efficient process or is that a big loss?
Every single time you convert anything, even you transfer or transmit energy from one point to another, or you convert energy from one form to another, there's always losses.
But how big of a loss?
How big of a loss? It depends on the magnitude of the voltage.
Like significant?
No. So a typical rectification is typically done through diodes, and it can be done through switches too, but they're going to have roughly the same drop. They're going to drop about 1 to 2 volts. So if we're talking about a 500 volt motor, however, that's not all that big of a deal. It's only a couple of percentage. And when I was at Virginia Tech, this is actually one of the things I worked on, was designing highly efficient power electronics, and specifically for fuel cell vehicles, what I worked on. And the challenges are that these electrical devices, no matter how good they are, will always have some kind of voltage drop. You'll always lose some potential. And of course, anytime we have lost energy like this, it becomes heat. So we have two challenges. We're losing some energy in this conversion process, and we've got heat to deal with. And so our group specifically dealt with reducing that loss as much as possible to get the highest efficiency and to have the lowest cooling requirements. And whereas most power electronics that you use, if you have a laptop here, you have a charger and it has a little box on it, right? That's a set of power electronics. Those are usually in the 80 to 90% range, whereas what we were dealing with was about 98 to 99%. Yes. Yes. That's right. Input to output. And I mean, that's at peak, but always considering things at their optimal point.
So it's advantageous to run on AC because it's so much more.
AC has so many advantages. I could spend an entire class on it, but the main point is you have an AC motor, you need to convert it to DC until we can make AC batteries. That'd be pretty cool. I don't know exactly how that would work, but hey, I always encourage my students, don't think just because this is the way things are, that's the way they'll always be. Like somebody had to think of the idea of hybrids to begin with. And someone had to think of a series hybrid, and then a parallel hybrid, and then a parallel series. And now we're getting into, in one of my textbooks, there's actually, I think, a University of Michigan architecture. And came up with their completely own design of how everything works and interacts. I'm like, sky's the limit, So, maybe there are different ways to do this. Maybe there's a new device out there to go from AC to DC. I don't know. I really don't know. Maybe there's a battery that can take AC. I mean, I throw ideas out all day long about these things because these are the challenges. And like I said, every time you convert or transmit energy from one point to another, you lose. And so how can we reduce those losses? And all kinds of innovations have led to increases in efficiency. And yeah. Oh, sorry. I
have one more question.
Yeah, go for it.
Which is the actual stopping of the vehicle.
Yes, right. I'm going to get to that, and I'm going to get to that in a second. But the thing to remember here is that this induction, maybe I skipped this when I was talking, but the induction in the motor creates an opposing torque. And that's what I was talking about. If you're moving your coil in your magnetic field, you're probably going to feel some resistance, some physical resistance to that. And that's that back EMF being created. So I've been trying to find someone to do animations for me to illustrate this point well enough, but I'm going to skip back for 1 second just to see if I can, I think I can use this well enough. So let's assume for a moment here that this battery is now removed from the system and the rotor is spinning freely because the vehicle is moving, and we let off the throttle, so there's no power being provided to this coil. And this is, by the way, a DC motor, so this would never be used in a hybrid vehicle, but that's okay. And so this rotor is freely spinning in here, except for the fact that this coil is moving through these magnetic fields created by these permanent magnets. All right, everybody with me there? Okay. So as this, if you take point A, which is where it is right now, there is some flux linkage. There is some magnetic field that is going through the cross-sectional area of this coil. And then, of course, our rotor is moving, so the instant it moves one tiny little bit, that magnetic field changes, so we have a change in flux linkage, and therefore we have a back EMF. We have some potential across the ends of this coil. And so current starts to flow. Everybody with me to that point? Okay, good, because this is where I have to swap back over. Now what happens if you take an electrical coil and run current through it? It creates a magnetic field. Okay, so that's where the the resistive force comes in. It's because, yeah, we're creating current to flow through this, and that's recharging our battery, and that's fantastic. But when current flows through this coil, it produces a magnetic field. And now we've got magnetic field here and magnetic field here interacting. So we're right back to where we were. The difference is in this case that when we're in regenerative mode and it's producing this back EMF flow, it's resisting. So in this case, it would become a south pole. And these are going to push against each other, right? And then as soon as it passes this point, it's going to flip, and it's going to become a north pole. And it's going to fight against this one until it hits here, and then it's going to flip and see a south pole.
Keep slowing down.
Exactly, and that's where the braking comes in. Whew. I always get nervous when I try to explain that because I'm like, yeah, I know I'm going to make some leaps in logic, but that's awesome. So applying all of that, right, this is that key point. This induction, inducing current in that coil, creates an opposing torque, and there's our braking. Yes, I guess I skipped the most critical part of that when I was explaining this list here. But so yeah, vehicle's in motion, it rotates the wheels, which rotates the electric motor, gets that rotor turning. The rotor turning induces current, recharges our batteries because we're rectifying it, putting it back in the battery, but it also creates this opposing force. And there's our braking.
So when you put your foot right hard on the brake, you're going to hard brake.
Mm-hmm.
I'm trying to visualize the picture of how
Beautiful.
How does that hard
I've got a
brake
visual for you.
stop completely?
Oh, I've got a visual for you because that's a fantastic question. Matter of fact, here it is.
Leading right up to it.
Yes, that's beautiful. I love it. I always try to anticipate the question because then what I'm talking about is led by the curiosity of, well, wait, is that enough? And the answer is no, it's not enough force. If you were just to have regenerative braking in a car, you'd probably be in trouble. Somebody slams on the brakes in front of you and you go, uh-oh, boom. Why? Because regenerative braking has a limit. It has a limit to how much reverse torque it can provide, even if we're controlling that, even if we're doing something to manipulate that braking. If we push it to its maximum, it's going to hit a point. So if you ignore these other two for a moment and you push further and further on the brake pedal, here it would be fine, here it would be fine, here it would be fine, because all of our braking is provided by the regeneration, the electric motor. Then you hit a point where you push harder and harder and harder on the pedal and it doesn't slow you down faster. And so what happens is we then balance in front wheel brakes and rear wheel brakes, and this is Ford's approach. Is they bring them in different ratios, so you can see that they grow pretty close to each other, but they bring it a little bit different. And so what we have is a balance now of the actual mechanical brakes with the regenerative. So there's only so much force we can get, and almost only so much of the kinetic energy that we can recover. And that's why in a hybrid, if you do a lot of heavy braking, like I know some of my friends in DC were complaining because they're like, I'm not getting very good gas mileage. That's because you guys go foot to the floor and then foot to the floor over and over and over on the Beltway. And if you've ever driven out there, you know exactly what I'm talking about. It's one, and you cannot recover all that. A lot of that's still going to go to mechanical braking, which is heat loss, and we cannot do anything with that at this point anyway, unless it's a cold day and you can cycle it into the car or something. But you know, it's just, there's not a way to use that waste energy right now. So you get your most benefit when you're operating right here in this range for braking pressure. And so, one other thing, sorry, one second, is that this is your stopping power. So if you look at the upper curve here, it's pretty linear. And that's what manufacturers design braking systems for, is so that all three of these try to balance and give you as linear of a feel as possible. So 50% brake pedal is half your braking power. So, yes, go ahead.
So then, mechanical braking, you're literally talking about like pressure on a cylinder, on a fluid.
Yep,
pushing-
drum brakes, disc
pushing
brakes,
the
yes.
rotor, or the calipers onto the rotor.
You got it.
So then, like when you actually come to zero velocity,
Mm-hmm.
and you're not spinning anymore, you don't have any more back EMF.
That's right.
So somehow the car has to reach out and squeeze the calipers
Oh, well,
for you, because you can't feel the different points in the brake pedal. It's like all been automated, so you can't
Yeah.
tell which part you're activating.
I guess there's one piece of inaccuracy here is that when you're at zero speed, you're usually sitting on the brake pedal about this much to keep yourself from rolling. That's all mechanical.
Right.
And so that's all going to be done through the fluid pressure, and you know maybe it's a new challenge now because the gas engine shuts off frequently, in these hybrids, right? And so that you're not spinning a brake pump, brake fluid pump. So you're probably, I think they're actually doing electric braking. I don't know. I just realized I'd never thought about that. When you're sitting in a stop, what's the clamping force? Is it just your fluid pressure?
Well, it's that transit. At
Is
like
that what it
2
is?
miles per hour, it has to go from.
Yeah. Well, you're right.
Let go of that regenerative and grab the.
That's right. At very, very low speed, this curve drops a little bit here for regen. At low speed, it's very hard to get any regenerative back force, resistive force. So, yep. What were you going to say?
Well, I was just going to say, if you look at a standard service brake system on a non-hybrid vehicle, the area in green and the area in orange there, that actually constitutes your front braking ratio versus the rear braking ratio in a hydraulic application. Okay, that entire area is all hydraulic.
So it would be
so this green
red and
portion here is taking some of the need for a hydraulic service brake system away. You still need to have that service brake system to bring it to a complete stop. Okay, so the whole intent is once, and I know Ford monitors angle of rotation in the motor to determine when to actually apply the service brake system. So you have an assembly that is an electronic master cylinder, the early ones, and they've gone away from that.
Right.
But the electronic master cylinder, you're not actually applying the service brake system. It's got 3 redundant sensors on it that indicate the pedal position and pedal force. Okay, the amount of pedal force indicates how fast do we need to stop. Same thing with pedal position. That goes to the control processor that would then apply the service brake system at varying rates based on need. But you never get away from the regen point. Once the vehicle is stopped, if you're in idle loading mode, the engine's not running, you actually don't have an effective torque against it. If you're on a flat ground, you could theoretically take your foot off the brake pedal altogether and the vehicle won't move. Okay, so
But if you're on a slope,
combination of service brake
yeah.
and regen braking
Yep.
going on all the time.
Right.
Okay, and pure regen is really used as an engine brake strategy, not necessarily a stop vehicle strategy. It's
a good point.
It applies to stock vehicle,
Right.
but it's really, its primary use is engine brake.
I mean, you can
So-
see
Yeah,
it.
you
Prius,
can.
you can.
Driving one.
Oh, yeah.
Driving to stop, it always does that.
Yeah,
Right.
you can feel
Where
it
it
kind of
switches
just
over.
have a little switch. It's still a little bumpy.
It's kind of weird.
So to summarize what you just said, and especially for the camera, is that this pedal pressure is being monitored electronically. It's not actually applying pressure to something, it's just a sensor. Determines 0% to 100% braking pedal. And the vehicle in a hybrid is determining how to distribute or how to effectuate that pedal pressure, that pedal pressure position. And so if we're about 50%, it's going to say, okay, push my regen to maximum, push my front wheel pressure to about half, and my rear wheel pressure to about half. And so that gives me the collective braking force that I'm looking for. And of course, one more thing you have to remember is regenerative brake torque is at the drive wheels. So if we're talking about a front wheel electric drive, then that's also going to be front wheel deceleration there too. So you're going to get some dive from that. Versus, I know some of the Lexus hybrid, the RX 400H and 450H, I think there is now, have four-wheel drive. And so they can use the rear electric motors as well to decelerate. So there's, of course, you consider how that affects the dynamics of the vehicle. Another whole challenge to making sure you have dive control and steering control in an emergency situation, understeer, oversteer. So this is a very simplified kind of diagram, probably what it would do in a really heavy braking situation. Is it's probably going to rebalance some of these things in certain ways to manage stability. But things get real complex nowadays. Cars are thinking so much for themselves. So what I want to do here real quick is to jump forward. I gotta bail out of here real soon, but and just show the four modes, or main modes, I guess you could call them, of a typical parallel hybrid vehicle. So in the first mode, moving off, which is another term for just starting off relatively slowly. First of all, about these diagrams, we have a gas engine. This is a battery, and the wheels. There's AMT, which is automatic transmission, and inverter, which is that key piece of power electronics between the battery and the DC battery and the AC motor. And so then there's our motor and there's our wheels and differential. And in every one of these examples here, in every one of these cases, the wheels are turning in the same direction. They're all going forward, so you don't have to worry about which way the wheels are turning. But in this first one, moving off, we're at a stop and we start going. It can be done very easily and very efficiently by sending power from the battery to the inverter, to the electric motor, and through the transmission to drive the wheels. And as I told you, like that electric motor has very high torque at 0 RPM, so that's a fantastic way to start off. Now, if you're drag racing and you're trying to get around the next guy to get on the highway, which we all do about once a week, right? Oh, I need to be in the right lane. So you put your foot down to get ahead of the guy next to you and turn off and get on the ramp. We get into this hard acceleration mode, and what happens is the clutch kicks in and combines the engine power with the electric motor power, so we get the maximum acceleration of the vehicle through the wheels. At cruising, we typically run strictly on gas engine power, and the reason for that, of course, is that gasoline engines run very well, very efficiently at cruising speed at a consistent speed. So that's still going to be our max efficiency. And of course, this is why if you drive a hybrid on the highway, you won't get any gain, because this looks like a normal car plus some heavy electronics, right? So you won't get a lot of gains from that. In fact, you could have some losses. And then finally, this is the one we've been talking about, is the slowing down phase. And what happens is, again, the wheels are still turning in the same direction, but they're turning through the transmission, they're turning the electric motor, and the electric motor is creating induction in those coils in the motor, which is making power flow. It goes into the inverter, comes in AC, goes out DC, and recharges our battery. Boom. We've just made something out of that kinetic energy that we didn't need anymore. We're going 70, getting off the exit ramp, I need to decelerate. Don't want to waste all the energy I just built up. Good. I put it back into the batteries to a percentage, right? This has losses. Oh, the heck with that. These have losses. These have losses. This has losses. This, and this. Every single one of those. What's the conversion? I think you can get, I think it's around 70 to 80% at the peak of, if you're at just the right speed for the motor, blah, 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 you can get about 70 to 80% of the kinetic energy converted to electrical, which is pretty good. Now, mind you, of course, as you slow down, that's going to continue to decrease until you get to a stop where it's zero. But there you have it. There's where regenerative braking fits in. Oh yeah, I forgot about this piece. Also, the question is going to be, a good question would be, well, how do we get this regen braking to go from 0 to full force? How do we control it? And this is specifically for an induction motor, but for a permanent magnet motor, it looks very similar. What we're usually doing is we're operating an induction motor in this range right here, and this is 0. Sorry, so this is a control parameter of an induction motor. Just kind of go with me because this is a control signal to the induction motor. So just, again, this is about a 3-day explanation to get to this graph. But I wanted to show you something. Yeah?
Could you describe the axes?
Yes, I will, yes. So slip is the control parameter for an induction motor. I can tell it what I want the slip to be. And the result is the torque. So typically what we're doing is we're saying, okay, 0 slip means 0 torque, or at some point between 0 and 1 is my maximum, and that's my maximum torque. So this is in the forward direction. This is I want 0 torque, I want full forward torque, I want something in the middle. I control this slip parameter. All I have to do is say slip equals 0.15, and boom, off goes the motor. That's all done through the control system. What we can also do in an induction motor, and this goes back to your question, which is what happens when you let off the pedal and you're drifting? Well, in an induction motor, nothing happens because by default, the slip goes to 0. And there's nothing going on. It's not even a motor. It's just a couple of pieces of metal spinning. But then, as soon as I send a little bit of signal to the induction motor, and in this case, I give it a negative slip, then it starts to push into negative torque. And so, if you, to translate this into what this means really quickly, this means that when I give it a negative slip, I'm actually sending some power to the induction motor to do braking. So yes, there is a little bit of loss in there. And that's required also for the permanent magnet motor. You have to send a little bit of power to the coils to get them to produce a bigger magnetic field to get a larger braking force. So yes, you're sending a little bit of energy to the motor to get anything above the default drifting, deceleration or regenerative braking. And so I can push it all the way down to its maximum negative torque to get that maximum point on our green curve, right? Remember the green curve, it comes up and hits that peak. That's what this is right here. So this is a controllable thing. All built into the motor control, and how we get there is, again, another one long lecture. So, question?
So if you were a car engineer and you wanted to give the operator some of that control because they're in hilly terrain,
yep.
they see something coming, you could have like a manual apply regenerative braking more or less.
Well, that's what the brakes are. I mean, that's what your brake pedal is. It takes that role completely because that's what we want to do. Is in the induction motor, if I'm going down the highway at 70 and I let my foot off the gas completely, it's going to go straight to this 0 point. Now, what auto manufacturers may want to do is to not give that feeling of 4,000 pounds just drifting down the highway. So they might automatically push it into a few percent of regen braking. So we give it just a really small negative slip command. And so therefore I get just a little bit of drag. And then of course, as you start to push the brake pedal, it's going to follow this edge right here. And the more I push, the more I push, the more regen I get until right about this point. What I think would be cool is when it tells you, if it were to tell you when your brakes were coming on. So I would say, oh, okay, I don't need to slow down faster than this, so I'll back off and get all regen. You know, I think that might be a cool thing to do. But I just wanted to show you how it's controllable, because that's a, you know, if I skip that completely, it'd be a gap. And well, wait, how do I get 50% braking? So yes.
Can you clarify something? Because I'm not
Mhm.
100% certain on AC induction machines.
Uh-huh.
Positive slip, we lead the signal, is that correct? So
Yeah.
negative slip would be retarding the signal
Mhm.
essentially, but actually would it be past? Or is it,
It'd be behind it.
it would be,
Mhm.
okay.
So the actual rotation of the rotor looks like this, and the electrical signal around the outside would be a little bit slower.
Okay.
So, and since it's a little bit slower, it's going to induce it's going to induce things behind the rotation and pull it backwards. Induction motors, I've designed what I call a super lecture for induction motors. I build up to it for about 3 or 4 days, and then I go back, and 3/4 of the class is just rehashing everything that I've taught up to that point. And the last quarter of the class is introducing induction motors. And if the end of the class they get it, it's like, oh, because induction motors are extremely complicated. They're all coils, there are no permanent magnets, and so you have to, and there's nothing connected to the rotor. There are no electrical connections into the rotor. So you have to induce electricity into the rotor to make it make a magnetic field, and then to interact with the stator at the same time. There's nothing simple about it. So that's why using this nice slip diagram is really good, because life is easy. So all we have to do is determine this slip signal between positive SM and negative SM, and boom, done. Whew. It's always an intense topic. There's just so much here to condense this down into as short a time as we've talked about it.
So drive down the road with your foot a little bit on the pedal, all on the gas.
It's 2-foot drive.
Oh, 2-foot driver. Yeah, right.
You purposely prime your battery.
There's actually what's called a through-the-road hybrid, which is like the 4-wheel drive Lexus I was talking about a few minutes ago. And I don't know how much is actually used, but it's the principle is that you use the gasoline engine to drive the front wheels, and the back wheels are coincidingly regenerating. And so you're actually charging the batteries using the gas engine through the road to drive the rear wheels, which are then regenerating back into the battery. And that's a different way of doing what the Prius does via the planetary gear set. The Prius takes the gas engine and drives it through the gear set to another generator and recharges the batteries. So it can be done. I would imagine that would be a dynamic nightmare, just because you've got a pulling force on the front wheels and you've got a dragging force on the rear wheels. And I mean, maybe if you have electronic suspension, you can make that balance out. But to me, it sounds like a nightmare. But I'm an EE, so I think the mechanical side is a little more scary to me. So, but yes, can be done, absolutely. So in conclusion, regen braking is just a property of electric motors. That's fantastic news. Why? Well, because first of all, it reduces the use of mechanical brakes, so that's waste heat that we're not generating. It's also materials that we're saving, because we're not burning up brake rotors and pads as frequently. Doesn't require any extra equipment, because it is just a property of electric motors. We're just using what's already there in a new way. It recovers kinetic energy that we don't need anymore. We don't need it because we need to slow down for whatever reason. And it recharges the batteries. And so when it recharges that battery, we can then, when we come to a stop or we need to reaccelerate, be used to drive the vehicle back up to speed. And so there's regenerative braking in a nutshell. That's a hyper-accelerated lesson, by the way. So if you're still spinning a little bit as to everything that just happened, no pun intended, then don't be surprised. Because again, I also talked about 2 completely different, not completely, but majorly different types of electric motors in this, and only kind of dabbled in how they actually operate in regen braking mode. So it is a very cool marketing tool, in my opinion. Something that people think, oh wow, that's a cool technology to add to a hybrid vehicle. But as you now know and can explain to students, well, yes, it's actually just a marketing tool. It's just a property of an electric motor. And you can take, in fact, if I had more time, I would have remembered that somewhere in the physics lab, they have these little hand crank motors. And it's an electric motor with a hand crank on the shaft. And so you can take it and plug it into a battery and the shaft will, the crank will turn. Or you can unplug it and crank it and you're regenerating. Now, of course, when the wires are just, open, not doing anything, you're not flowing any current. So the cool trick is that you take the two wires and you clamp them to each other, right? Which is the shorted rotor test. And then you try to crank and it is so much more difficult. This one time and one student broke the crank, right? So the principle here is that shows you the difference between the free drifting kind of turn of the motor and that maximum point I was talking about a minute ago, that maximum negative torque. And if you control that, then you can control the braking force from 0 to maximum. And so there's what we have, regen braking. So, any other quick questions before I have to run out of here? Yes, sir.
You've got an internal combustion engine, which is pistons and valves, and it's essentially an air compressor. Why can't you push your exhaust into some kind of tank and then revalve it back in to give you this?
There actually is such a system.
Oh, there is?
There is. Yeah, it's, I forgot, it's a form of pneumatic hybrid, basically. And I was just looking at this yesterday. I forgot where. Oh, I know. I was looking for good images to use in this, and I saw a picture of one. I was like, oh yeah, that's right. But it's exactly the principle. Is it's kind of like on semi trucks. They use compression braking, right. And you know when a truck's using that, right? They actually have signs up around in some towns that say no Jake braking because they're so loud. But it's using that compression as the decelerating agent. Of course, that pressure isn't going anywhere, unfortunately. And so what you're talking about is where we capture that pressure that's generated in a tank. And for diesel, it's massive, so it's a fantastic thing to capture. And it slows us down, and we can reuse that to some degree. So, yep. Awesome. And see, this is exactly what I do in my class, is I talk about this specific type of hybrid. This gasoline engine, I hardly talk about diesels, and electric motor with a battery as the means of making a hybrid. But very quickly the conversation drifts off into what about fuel cells? And then what about flywheels? And what about pneumatics and hydraulics? And all of a sudden all these things come into play. And I'm like, this is exactly what an engineer should be doing. It should be thinking about all these different ways to capture energy and to reuse it. And Dr. Bradley, I think you guys are still going to see him again this week. No, is he done? Oh, okay. Well, he always tells a story, maybe he already did already, about they were testing a flywheel on a bus, and it was one of the early models. And as I remember the story right, it went that they were testing it on the track and they were rolling it up and down, and it was working great. I said, let's really try this thing out and see how much energy it can regenerate. So they get going full speed and slam on the brakes really hard, and the bus comes to a halt, and they're like, yay, it did it. And then boom, and the flywheel comes rolling out the side of this thing and just takes off down the road because it had so much energy in it that it broke the bearings loose and just busted out the side of the bus and took off. And so, there's always scary things when we talk about hydrogen fuel cells, or like, oh, the hydrogen tank might explode, or the flywheel that, the flywheel might come flying out the side, and then there's, for the hybrids, it's, in an impact, the battery fluid might leak everywhere. So all kinds of safety concerns, all kinds of things that the general public needs to get over, but in reflection, they had the same challenge when gasoline vehicles came about too. So it's, all kinds of different ways. And also one of those air pressure tanks going, it sounds like a bomb going off. High pressure tank with 10,000 PSI, boom!
10,000.
Well, it depends on what you're doing with it, but yes. Our hydrogen tanks are running at 4,000 or 5,000. So.
Yeah, scuba tanks hold 3 to 5.
Mm-hmm.
Why not?
Yeah, right. So, It's crazy stuff. It's good times, especially if you like to blow stuff up and go big or go home kind of attitude, you know. So, any other quick questions before I
Fuel
run?
cells can go backwards, right?
Fuel cells are also bidirectional.
So
They're
if you
much.
generated electricity, you could make hydrogen?
That's correct.
Wow.
Nope. They do reversible
But then
electrolysis.
you'd have to compress it to store it
That's the challenge.
or blow up.
Yep. There's actually a little toy kit car that I played with at one of the national labs. This is a long time ago when fuel cells were still a blip on the radar. But what you do is you fill these 2 little tanks with water on either side, and it's got to be distilled water, of course. And those are hooked run to the fuel cell. And then the output of the fuel cell, the electrical output, has just 2 little banana plugs, and you plug in this little solar cell, and you set it up on there and set it in the sun, and you give it a few minutes, and you watch, and the 2 tanks, one on one side, one on the other, one says H2 on it, and the other one says O. And of course, the H2 one will completely push all the water, or use all the water and convert it into hydrogen, and the oxygen one will get halfway, right, because of molecular balance. And so once you get to that point, you unplug the solar cell, and you plug in the electric motor on the cart, and you wait, and you wait. And about a minute or 2 later, the process reverses, and then some power starts to flow, and the cart goes and takes off. But that's the problem, is that the reversibility of fuel cells is tremendously slow. And that's one of the big reasons that you don't see fuel cell vehicles used in a regenerative sense. It's just simply because, well, not only about storing the hydrogen at pressure, but because of that slow reversibility. And one of the projects I also worked on at Virginia Tech was making sure that no power ever backflowed into the fuel cell. And it's surprisingly difficult when you're driving an AC motor, because the load is always doing this. It's the nature of it. And so there's always a little bit of backflow that, you know, the fuel cell starts pushing out, and then no, it pulls back in a little bit, pushes out. So our control systems, one of my colleagues actually patented this, was designed to flatten that out, and from the fuel cell's perspective, to reduce the ripple current. But yeah, I mean, right, and this is the cool thing about all these technologies, is every one of them has their strengths and weaknesses. And I'd just love to see somebody make a hybrid out of every one of these. I think it would be the coolest project ever, just to have all of these different mechanisms all in one, so you could see them all in operation and how they interact, and the fact that they can all operate in parallel, simultaneously with each other. So